Well, hello, and welcome to a module about heat exchanger effectiveness. So whether you're in ME 2134 thermodynamics or ME 3204 heat transfer, this can apply to you if you're interested in learning a little bit more about how heat exchangers perform. So I've created a little model of a very classic, this would be called a counterflow heat exchanger, in which we might have hot fluid coming into this copper tube that's centrally located inside this PVC pipe. Okay, so we've got a hot fluid coming in and a hot fluid leaving, but it's cooling down because what's surrounding that copper tube would be cold fluid. We'd have cold fluid, cold water, say, coming in, absorbing heat from the hot fluid and coming out here. And so this is just a model of a very simple counterflow, what we call two-pipe heat exchanger. And so the idea is, for this module, is a way to quantify the effectiveness of the heat exchanger. Basically, in other words, how well it's working compared to the best it could possibly do. So let's go ahead and get started. Okay, and so notice here that I'm going to try to explain the difference between effectiveness, what we're interested in quantifying here, compared to efficiency, which in thermodynamics class, you've had a lot of experience in so far. You've got things like pump efficiency, turbine efficiency, compressor efficiency. So you've had thermal efficiency. You've had all these things. And so the idea is, why would I want to introduce to you folks the idea of effectiveness of a heat exchanger? That's going to require a little bit of a crash course in heat exchangers, which may benefit ME 3204 folks as well. We will define what's the definition of heat exchanger effectiveness, and then we'll go through an example problem to determine the effectiveness of a heat exchanger. Okay, well, why go through this in the first place for thermodynamics students? Well, there's a classic homework problem that's assigned in most of the sections. Problem 945 has to do with a Brayton cycle, a model of a gas turbine engine. And you've learned that, wow, the exhaust from a gas turbine engine is very, very hot exhaust gas. And so in this problem 945, it says the exhaust gas stream is fitted with a regenerator, and the regenerator effectiveness is 85%. Now, what in the world does all that mean? So you haven't really been exposed to that yet. So the two questions then to work on this homework problem is, what is a regenerator in the first place? And what is effectiveness? It says it's 85%, but I don't have any idea what that means. And is this a lot like thermal efficiency of a cycle? Is it like a turbine efficiency, pump efficiency, compressor efficiency? And the answer is no, it's not like that at all. Okay, so diving into problem 945, this would be a sketch, start with a sketch of the problem. Here's the classic model of the Brayton cycle: compressor hooked up to a turbine, and then that turbine is making power, and it's making more power than it takes to drive the compressor. And so typically the net power would go to, say, running an electric generator. Here's the combustion chamber that's providing the heat to power the turbine. Now, so the turbine exhaust, very hot exhaust gas, as you can see from drawing the TS diagram of the cycle. We won't go into those details. I hope you recognize it as, yeah, I think I could do this on my own. I could draw a TS diagram of this Brayton cycle on my own. But problem 945 is particularly tough because this exhaust gas is coming into a heat exchanger. And so the hot exhaust gas is cooling down from 4 to state Y. And at the same time, what the gas that's coming out of the compressor, the air, at state 2 is being heated up to state X. So that's a regenerator. That's the purpose of a regenerator, is to recover energy from a hot waste stream, and that improves the effectiveness of the overall thermal system that you're trying to operate here. So that's what a regenerator is all about. It's an energy recovery device. Okay. So for this Brayton cycle, we've got an air-to-air regenerator. Air-to-air regenerator. Now, what would that look like? Well, basically, it would look like a big duct, and inside that duct are metal plates that are fabricated so that the hot exhaust stream does not mix with the incoming cold air stream. So let's quickly look at this sketch, okay? This would be sort of the thing that looks like a duct. The red arrow, state 4, hot exhaust air is coming in. It's ducted through this system of metal plates that will conduct the heat away. So it's going to be cooled down some to state Y. I'm showing it as orange. It's not going to be room temperature. It's still going to be hot, but we're going to recover energy. We're going to recover energy from this hot exhaust gas from state 4 to state Y. How do we do that? Well, we come in with cold air or cooler air, state 2, and it's picking up energy from the hot stream. And so you see that I've colored it yellow to show it's kind of warmer than blue. And off it goes then to the combustion chamber. So be aware, for a regenerator, air-to-air regenerator, the two streams do not mix. 2 to X does not mix with 4 to Y. Okay. Now, my little assistant is coming over to help me, so he may appear in the screen. So we'll just kind of watch my little assistant. I'll try to watch him out of the corner of my eye. And here he is. There is Tigger. Here is my little assistant, Tigger. And so glad to get him on the video. And I'm going to try to put him down so he doesn't walk on my keyboard and goof things up. So there's little Tigger. Down you go. Okay. Well, after Tigger's little visit, need to go through a quick crash course on heat exchangers. So for those of you in ME 3204, I'm hoping that this may be familiar to you. If not, I hope you get something out of it. But for ME 2134, this is looking ahead to your ME 3204 heat transfer course. So the basic objective of any heat exchanger is to transfer energy from one flowing fluid to another flowing fluid. That's the purpose of a heat exchanger. That's the purpose of this heat exchanger. Okay. What's the key point? Well, to get heat transfer from a hot fluid to a cold fluid, you must have delta T. You must have a temperature difference between the two fluids. Now, how would we model, if we're in thermo or heat transfer, how would we model the situation? Well, looks like an open system because I've got flow entering and leaving. Okay. I've got steady state, steady flow. In other words, at all times, the hot fluid coming into the exchanger is constant, as well as leaving. Same with the cold. At all time, the flow is steady. It's not changing in time. Usually, we've got 2 inlets and 2 outlets, usually 2 inlets and 2 outlets. So multiple inlets and multiple outlets, and recognize that the streams do not mix. Okay, that's sort of step 1. Basic objective of heat exchangers: exchange energy between a hot fluid and a cold fluid. I've done a little introduction to heat exchangers in this video, and so suggest that you might, if you're interested, go offline and watch this video as well, Introduction to Heat Exchangers. There's a picture of me demonstrating the heat exchanger model. Okay. Jargon. Basic 2-pipe heat exchanger, where I created this model. So notice here that for the model, this PVC makes up the shell of the heat exchanger. We call this, so what's flowing into this PVC shell, and what's flowing out of, that's called the shell side flow. Now, what's coming into the middle, into this copper tube, it's called the tube side flow. So it's just very common sense jargon, tube side flow and shell side flow. There are two basic types of two-pipe heat exchangers. One's called parallel flow, and I find that the easiest to understand. A little more complexity is called counterflow. So let's look at the parallel flow first. Notice here in our two pipes, we've got the hot going in and the cold going in on the same side of the exchanger. Okay, so both of those are coming in. They're flowing in parallel. Tube side and shell side are flowing in parallel and coming out the other side. Okay, that's pretty easy to understand. So obviously, with the hot in and cold in, so do you see that the biggest temperature difference here is at the inlet? And do you see that the hot fluid's cooling down, the cold fluid's warming up? And so as you get to the outlet of this exchanger, the temperature difference is not going to be nearly as high. Okay, so I think you got it. Counterflow, a little more complexity. We've got the hot fluid coming in one side and the cold fluid coming in the other side. And so do you see that the two streams are flowing counter to each other? We call it counterflow. And we perform classic thermodynamics first law analysis on either of these. How do we start with a sketch, open system, steady state, steady flow, two inlets and two outlets. There's no mixing, okay? Only heat transfer. There's no output or input power. There's no shaft associated with a heat exchanger. It's not lifting a weight, okay? And then the heat transfer, it depends on the way you draw your control volumes. So do you see that in thermo class, if you drew a control volume around this entire piece of equipment, around the entire piece, and you knew that you had insulation totally wrapping the whole heat exchanger, fully insulated shell, okay? Do you see that there'd be no heat transfer either? You'd simply have two inlets and two outlets, no heat transfer, no work, no heat. However, if you drew your control surface around only the tube side, do you see that you would have heat transfer from the hot fluid into the cold fluid? So there's three ways to express the first law of thermodynamics. Here's the first way, okay? It says that m dot hot times H1 minus H2 equals m dot cold. And I've sort of simplified that, right? So in other words, the sum of Q dot in, 0, minus W dot out, 0 for the whole system, the whole open system, equals the sum of the m dot leaving minus the sum of the m dot entering. I didn't show all those steps, but that's a statement of the first law. Similarly, if you just look at the first law for the cold fluid, you'd see Q dot into the cold is equal to m dot of the cold fluid times H4 minus H3. And similarly, the heat transfer leaving the hot fluid is m dot of the hot fluid times H1 minus H2. So my suggestion is you should be able to do this in your sleep. As we move into ME 3104, we introduce the idea of a temperature map. And so in thermodynamics, you've gotten good at drawing these sketches, either parallel flow or counterflow. In ME 3204, we introduced the idea of a temperature map. So notice here, for parallel flow, we on the y-axis, we plot temperature. On the x-axis, we plot position, x. So do you see the similarity? For parallel flow, we've got state 1 and state 3, both going in, hot fluid, T1, cold fluid, T3. Look at that. The maximum delta T is right here going in for parallel flow. As the two fluids flow in the exchanger, they exchange heat, hot to cold. The cold gets hotter, okay? And so ultimately, T4, what's coming, the cold gets hotter and the hot gets colder, okay? Easy to see. So the delta T is the smallest here. Now, a little more complexity, counterflow. Let's look at the hot fluid. It's coming in at hot at state 1. It's cooling down, leaving at state 2. Wow, but the cold fluid is coming in cold at state 3 over here on the right-hand side, and it's warming up because of delta T. So it's warming up to T4. Okay. Counterflow. Pretty easy to understand in your crash course. We're getting there to effectiveness. Let's take a little second law of thermodynamics quiz for those of you in thermodynamics class. So first question is, here's our parallel flow temperature map. Hot fluid, cold fluid. And the question is, can T4 ever be bigger than T2? Can you get T4 bigger than T2? Think of that in your mind. Now, let's go to counterflow, where the two flows are going counter to each other. Question is, okay, so I've got my cold out T4, hot in T1. Question is, can T4 be bigger than T2? Wow, can T4 be bigger than T2? I don't know. Can T4 ever be bigger than T1? Can you get the temperature of 4 bigger than T1? Can T2, last question, can T2 ever be less than T3? Can T2 ever be down here? So those are questions. If you had a quiz, could you answer all 4 of those questions? Let's look at the answers. Can T4 ever be bigger than T2 over here? Well, the answer is no. That would violate the second law. You can't ever, for this parallel flow situation, you couldn't heat the cold fluid up higher than the hot fluid. So no, that would violate the second law. Okay. Can T4 ever be bigger than T2? And the answer is yes, it can. Okay. There's nothing to prevent T4 from being a bigger, hotter value than the hot coming out. It just cannot be bigger than the hot coming in. That would violate the second law. Similarly, T2 cannot be less than T3. You can't cool the hot down below the coldest cold. So no, you can't have that. That would violate the second law. Okay. It is my hope that you feel pretty good about that, even without being a second law expert. It's my hope that your common sense will lead you to the answer to these questions. So here's some practical conclusions about the second law. So what I've shown on this slide are impossible things. So it is impossible for, in parallel flow heat exchangers, for these two lines on the temperature map to cross. That's impossible. Okay. Similarly, in counterflow situations, it is impossible for these lines on the temperature map to cross. You can never get the cold fluid hotter than the hottest hot fluid. Okay. Feel pretty good? You feel pretty good about that? I hope you do. So that's a big takeaway, both for thermodynamics students and heat transfer students. These temperature map lines cannot cross because that would indicate a violation of the second law. Okay, so finally, what's the definition of heat exchanger effectiveness? So here's the definition. Effectiveness that we call in heat transfer class epsilon, Greek letter epsilon. It's the actual heat transfer from the hot to the cold, the actual heat transfer divided by the maximum possible heat transfer from hot to cold. Actual divided by maximum possible. Okay. So in many real world situations, we can make measurements in the field. We can make measurements on our piece of equipment. And usually we have enough given information that we can determine the actual heat transfer. Typically in the world, we have values for m dot. And we have, at least we might have values for, let's say, the cold coming in and the cold going out. Okay. We've usually got a pretty good handle on the given data, not all of it, but some of it. So it's usually easy to determine the actual heat transfer using the first law. Okay. So there's a key point about effectiveness. So again, I'm going to repeat the definition. Actual heat transfer, we can usually calculate that, divided by the maximum possible heat transfer. All right, that's going to be a little tougher to decide. I do want you to realize, though, do you see that effectiveness, this definition of effectiveness, is different than efficiency? Typically, we insulate our heat exchangers so that the shell side, if it's hot, for example, or warm, is prevented from transferring heat to the surroundings. So we typically fully insulate our heat exchangers. And so do you see that in terms of efficiency and heat transfer, do you see that all of the heat for a well-insulated heat exchanger, all of the heat leaving the hot fluid goes into the cold fluid? So basically, it's 100% efficient, but not necessarily 100% effective. Okay, so that's an important thing for students to understand. Heat exchangers, for well-insulated heat exchangers, 100% of the heat leaving the hot goes into the cold. Okay, so now how to determine the denominator or maximum possible heat transfer? Here's what you have to do. You have to study two possible situations. Situation one, this will be a what if situation. What if the cold fluid is heated up to the hot inlet temperature? In other words, you heat the cold fluid up to the maximum possible hot in temperature. That's situation one. It's sort of a theoretical study. Situation two, determine the heat transfer if the hot fluid is cooled down to the coldest temperature. In other words, the cold in temperature. That'd be a second study that you've got to perform. So you got to do two what if situations. And then you can make some second law arguments to say the maximum possible heat transfer is the minimum of situation one or situation two. In other words, you do two theoretical studies. The maximum possible heat transfer, according to the second law, will be the minimum of either of these two. Simple as that. So now you've got the heat exchanger effectiveness. Once you've done your study of these two possible situations, you've determined the denominator of the effectiveness definition, and then now you've got a number for the effectiveness that's going to be somewhere between 0, not effective at all, up to 100%. It's 100% effectiveness is the best you can possibly do in terms of recovering heat from a hot stream and getting it into the cold stream. Okay, woo! An example problem. This is not going to be problem 945. It's going to be a simpler problem where we're exchanging hot exhaust gas heat with feed water, cold feed water. So here's our example problem for this. A finned tube cross-flow heat exchanger uses the exhaust gas of a turbine, so we've got exhaust gas in, exhaust gas out, to heat pressurized feed water. Okay, we're heating pressurized feed water at a pressure of 1 megapascal, pretty high pressure feed water. Now, field measurements, we've made some field measurements, and we've got some measurement. Exhaust gas flow rate is 1.5 kilograms per second. Exhaust gas flow, 1.5 kilograms per second. inlet temperature, 325 degrees C. That's hot. Now, we've also measured the feed water flow rate, 1/2 kilogram per second at a pressure of 1 MPa, that's the feed water pressure, an inlet temperature of 25 degrees C, and we're heating that feed water up to 125 degrees C. So we're getting 100 degrees C temperature increase. For the exhaust gas, we're going to model the exhaust gas as the ideal gas air with a constant specific heat of Cp equals 1.04 kilojoules per kilogram degree K. And what's our job? Our job is to determine the heat transfer from the exhaust gas to the feed water and the heat exchanger effectiveness. So we're looking for two things. What is the actual heat transfer from the exhaust gas into the feed water? And what is the heat exchanger effectiveness? Okay, so here's going to be our approach. If we study what's given, okay, we're given feed water flow rate, m dot of the water. We're given the feed water inlet temperature, and we're given the feed water outlet temperature. Do you see that you can look, that gives you the inlet and outlet enthalpy of the water. You've got m dot of the water. Okay. You know that there's no work involved. So do you see that you can apply the first law of thermodynamics for the water heating to get the actual heat transfer rate just from the given information? The amount of heat transfer into the feed water exactly equals the heat transfer leaving the exhaust. So that's going to be pretty easy to determine the heat transfer from the exhaust gas. Okay. The effectiveness, we're going to have to study two situations, pick the minimum one. That'll give us the denominator, Q dot maximum possible, and then we'll have our effectiveness. So let's get started with the example. Okay. Let's start with a sketch. We've got exhaust gas coming in at state 1 and leaving at state 2, exhaust gas, okay? I'm going to show the heated water coming in at state 3 nearest the coldest exhaust gas out. And I'm going to show the water coming out at state 4 coming out where the exhaust gas comes in. And what we're going to do is draw our temperature map as if, now this is cross flow. Do you see how the flow is actually in cross flow? It's not purely parallel and it's not purely counterflow. It's in between, it's cross flow. So in ME 3204, we draw this as a counterflow heat exchanger map. So we've got T1 to T2, exhaust gas getting cooler, and T3 to 4 in cross flow, water getting hotter. Okay, so delta T at state 1 early on up here is T1 minus T4, and delta T here is T2 minus T3. Okay. There's our temperature map. So we're going to study two situations. First thing we'll do is determine the actual heat transfer. We've studied the input data. We've got our feed water inlet temperatures. We will go to our steam tables and look up H sub F at T3 and H sub F at T4 and write those numbers down. We'll write down our m dot. We'll use our first law, W dot equals 0, to see that Q dot into the water is equal to m dot times H4 minus H3, and numerically that's 210 kilowatts. So we've got an immediate answer for the heat transfer into the water, which exactly equals the heat transfer out of the exhaust gas. There's just a little demonstration of how do we get our enthalpies. We go to our temperature table. Determine the exhaust gas outlet temperature. Wow, well, if we have the heat transfer going into the exhaust, we can write the first law for the exhaust gas. Q dot into the exhaust, it's going to be a negative number, isn't it? Equals minus W dot, that's 0, equals m dot of the air times Cp of the air times T2 minus T1. Outlet temperature minus inlet temperature. Cp is constant. That's the way we get our enthalpy change of the exhaust gas. So we can solve flat out for T2, okay? And so T2 is going to be a colder number than T1. And so sure enough, we'll do the math to get T2 is 190 degrees C of exhaust gas leaving, okay? That was pretty easy. It's a thermo problem. The next thing we'll do to get the effectiveness of our heat exchanger, we've got to study two situations. Let's look at the first situation. What's the maximum possible heat transfer for the water? In other words, we want to bring the water up to the inlet temperature of the exhaust. That's the most we could possibly heat the water up. So here's our m dot water. Okay. Here's going to be our T4 max. In other words, the max of the exhaust gas inlet temperature. We need to go back out and look at H4 max. We'll use our H sub F at T4 max. We'll write down that number 1478. That's a very high enthalpy. Wow. And we'll apply the first law for the cold fluid. Q dot max is equal to 686 kW. In other words, the maximum heat transfer we could get into the whole fluid be 686 kilowatts. Now we're going to study the second theoretical situation. What's the maximum possible heat transfer that we could get out of the exhaust? In other words, cool the exhaust down to the inlet water temperature. That's the coldest we could get the exhaust gas, okay? And so the coldest T2 minimum is 25 degrees C. That's the inlet of the cold fluid. So we've got an ideal gas with constant specific heat. We'll apply our first law for the air and solve for Q dot maximum from the air, 468 kilowatts. So we've got to make a choice. We will pick the minimum. In order to satisfy the second law of thermo, we pick the minimum value. So Q dot max is 468 kilowatts. And here it is. Q dot max is 400, the minimum of those two values. Wow, we're near the end of our example problem. We've got the denominator of the effectiveness, Q dot max. A couple of minutes ago, we calculated Q dot actual. So the effectiveness is 210 divided by 468, or the effectiveness is 45%. And so for this example heat recovery situation, we have a heat exchanger that has a 45% effectiveness. And that's our answer. Okay. So, and you say, well, wow, that doesn't sound so good. But it is what it is. We made some field measurements. And so our answer is that the heat exchanger that we implemented is 45% of the best you could possibly do. Okay. There would be some potential engineering explorations on how would we make it more effective, and we'd save that for another video. So what kind of recap do we have? So effectiveness is different than efficiency. That's a key takeaway. It's fairly easy to remember the definition of heat exchanger effectiveness. Epsilon is the actual heat transfer divided by the maximum possible heat transfer. Has to do with the second law. In order to get the denominator, we have to study two separate situations to determine the maximum possible heat transfer. It goes quickly, but we have to study two of those. And then have you seen in this example, have you seen this in this video, that you're nearly always using the first law of thermodynamics for open systems, for most thermal systems analysis, and you do it over and over and over again. And that's kind of an important takeaway, is that you've got to be really, really familiar with the first law of thermodynamics, particularly for open systems, to be a successful practicing engineer. So there you go. I hope that you've gotten something out of this video. What's heat exchanger effectiveness all about? What is a regenerator when it comes to recovering waste heat? And I hope that gives you, for thermo students, ME 2134, I hope it gives you a little picture or an introduction into what do we have ahead of us in ME 3204 heat transfer. Okay, hope to see you again soon.